All right, I have started sharing my screen. I hope it's visible to all. Great. Hello, everyone. Good afternoon. Welcome to today's webinar. We're going to be talking about Dockers and containerization and all of the good stuff. Before that, a quick introduction of DevLabs Alliance as well as myself before we get into containers. DevLabs Alliance is an organization that is a place of collaboration for all of us like-minded people who are very passionate about technology, very passionate about learning, very passionate of getting things done. And they have a host of trainings, offerings, these are classroom trainings, live virtual classes, whether it is testing or toolkits, whether best practices of DevOps, Hadoop, AI, data science, Internet of Things, blockchain, or practices for Agile, Safe, Scrum. And they have a couple of upcoming trainings and certifications. If you guys are interested in enrolling, these are some of the upcoming webinars as well as trainings they have. And you can reach out to them on training at DevLab Alliance, or you can visit their website, devlabsalliance.com. So that's a little bit about DevLabs, and that's me, Manika. I'm going to be your trainer for today, though I feel this is more of a collaborative learning than me being a trainer and the other way around. But this is a little bit about me. I'm a certified Scrum practitioner. That makes me a certified Scrum master as well as a certified product owner. I'm completing 25 years of experience in this month, so that's a long time. I started my career as a software developer, moved on to taking different roles across different organizations. I held the role of an enterprise architect for close to 15 years across different companies. Then moved on to heading business units, heading deliveries, heading India IT center also for one of the UK's insurance companies. Presently, I'm a freelancer. I don't do any of that now. I mean, I'm close to technology, but I'm more close to technology now. I do trainings, I do consulting, coaching on DevOps, Agile, blockchain, again, one of the areas that I'm very passionate about. And I work as a freelancer or as a consultant, as a developer also for companies or projects. And of course, I do trainings as well. I do trainings on different tools in the DevOps toolkit, Docker being one of those. That's what we are here for today. And other tools like Jenkins, Puppet, configuration management, continuous integration, and all of that. And when I'm not doing that, I also conduct meetups for Agile, Scrum, DevOps in the Delhi NCR region. So if you're ever here, you're interested in finding out if there's a meetup happening, please drop by. All right. So with that, let us move to our topic of the day, which is containerization. So we'll begin with a bit of an introduction of virtualization and how virtualization led to containers or containerization as we know that today. So this is how our hardware, this is how our computers have grown from a traditional architecture where we had a computer, we would have a computer, it would have an operating system, and we'd install a bunch of applications, softwares on that. Now, one computer would be designated to, or one computer would be used with one operating system and a bunch of software applications installed on that. Anytime we had to migrate any application from one version to another, that required us to upgrade, update anything else on that machine, or even the operating system version, if had to be upgraded, we ended up in situations like where some other software applications stopped working, or the other application also had to be upgraded, or it was deemed useless or not usable, not useless. And from a one-on-one mapping to our software applications to one computer was fine at the beginning when we started writing softwares and started using computers. But as the software writing became more and more complex, the requirements of or needs of our end customers became more and more complex. There came a requirement where we could utilize our underlying resources, where we could utilize our hardware resources, our computers, servers in a better way, without having to disturb, without having to upgrade the entire ecosystem that a software application that we were running or we created, and we hosted that in a production server. And the need for that essentially led for us to find out virtualization. So virtualization remains a very important technique, and virtualization as such is been around for more than 20 years now. The company VMware, which is primarily into virtualization and virtualization related software products, has been around for more than 20 years. So sure, virtualization has been around for since longer than that. We'll see how virtualization technology, especially on the Intel chipset, progressed, and what the interplay between the hardware support, the host operating system, the hypervisor, and the guest operating system of all of these virtual machines running on that. So what we achieved with first set of virtualization was use a set of infrastructure, use a computer or a server with a operating system, any operating system for that matter, and specialized softwares called hypervisors. Hypervisors essentially are softwares that enable virtualization, or that make virtualization possible on a computer, on a server. With help of these hypervisors, we were able to run multiple virtual computers, multiple virtual machines on a single server, on a single computer. These virtual machines could have their own operating systems, could have their own libraries and binaries, and we could install whatever software, whatever applications we wanted to install in every virtual machine. One of the benefits that we got was anytime I upgraded application 1 in this virtual machine, that did not impact my application 2 running in another virtual machine, because these were like totally separate computers, totally different computers, however, utilizing the same underlying host computer and working on a set of host operating system. Each of these virtual machines could have their own operating systems, and these operating systems could be anything. It did not have to be the same as the host operating system. We could run a Linux guest OS on a Windows host, or we could run a Windows guest OS on a Linux host. And that definitely led to much better utilization of resources and much better isolation of applications with an upgrade or an update to one of those, not impacting the other one. So this solved a lot of our problems, but like you say, you solve a problem and then you have newer problems, then you have newer challenges. And of course, as technologies grow, as markets grow, as economies grow, as businesses grow, of course, our requirement, our need from technology also keeps growing with that. So there were a lot of challenges we started to face even with this virtualization. technology where we were running different operating system, even different versions of operating systems. And again, we could not ignore this because of the complexities of modern business processing that relied on a large variety of software and hardware. And moreover, this complexity did not end with operating systems. Even if for a minute we could imagine a complete standardization of hardware and OS, there would still be challenge of managing the software and optimally managing the underlying resources, the underlying computer. Now, virtual machines enabled this isolation, but virtual machines had a huge resource requirement from the underlying computer. Virtual machines, we learned to create virtual machines as different files, OVA files, and we started to create virtual machine images. However, these files used to be ended up being very, very big, very huge files, which theoretically, yes, we could move them. Practically, conceptually, we could really not move them that easily. Moving a virtual machine actually meant breaking it down into smaller chunks of files and moving all those chunks of file and then using softwares to bring those chunks together. Auto scaling of our applications, auto scaling up of our applications was possible, but again, not as fast, not as efficient as we wanted it to be. It still took us anything from 6 to 8 hours to spin up a new virtual machine, install all the necessary softwares in that, install our application, and add it to a load balancer to scale up our application. These virtual machines were very, very resource intensive. Of course, they gave us the benefit of running multiple virtual machines on the same server, but each of the virtual machines ended up being very resource intensive. Since these virtual machines still had a complete operating system, still were a complete machine, switching them on and switching them off used to be not a very not a very easy, not a very short task. I wouldn't say it was particularly difficult, but any virtual machine for a project, for a business project like the kind we work on, would have a size of a couple of 100 GB and would take about 8 to 10 minutes to be turned on, and another 7 to 8 minutes to turn off. So yes, these were some of the things that started to become a challenge with the utilization of virtual machines and all of that. So from there, we further moved virtualization. We further enhanced virtualization by bringing in operating system virtualization in the form of containers. So here we could use a single machine, a single server with an operating system. However, this time, instead of a hypervisor, we started to work with a container engine, something like a Docker, a container platform, a containerization platform. And Docker enabled us to run multiple containers. I can call a container as a virtual appliance. I would not call it a virtual machine because it is not a virtual machine, but we call it a virtual appliance. And in a container platform like Docker, I could run many of these. I can run many of these virtual appliances, and every container has would give me the same behavior, give me the same, would exhibit the same traits like a virtual machine would. Like it would have its own operating system. I could install all the softwares or the libraries and binaries in that, and I could also host my own or deploy my own software application in that. Some of the advantages, some of the benefits, some of the challenges that coming from virtual machines we were able to solve with containers, or we are able to solve with containers, is they're very lightweight. The footprint is really, really small. They're not as resource intensive as our virtual machines are. It takes a couple of seconds for a new container to fire up. So the longest that I have seen a production container to start is 7 seconds. So with that kind of startup time, I can in reality talk about an auto scaling up and auto scaling down, where it just takes a couple of seconds to spin up a new instance of my software application. So this virtual machines, like I said, they've been around for a very long time. They've been around since the 1960s. Is the first time Linux virtualization started. Linux virtualization allowed multitasking between programs. Each program appeared to have a full access to the underlying machine, and VMware is a significant player in the virtualization space. So virtual machines are still a very good way of setting up well-defined environments. You can just copy the VM. There's really no need to install softwares on machines. You can have multiple different operating systems running on the same machine at any given point in time. And there was also an era where we started exploring boot machines, but virtual machines completely replaced the boot machines. Yeah, these are some of the challenges that I earlier mentioned that virtual machines ran into. These are still full operating systems. We still required a full Windows or a full Linux to be installed, from a distributed ISO image, and then application softwares needed to be installed on that, on top of that, and application softwares needed to be configured on that. And these are very large files. Like these can go into a couple of hundred gigabytes for a project. That if you want to take something live into production, and like I was mentioning earlier, if you need to move these can be moved into chunks of 2 gigabyte for FTP purpose, or for transferring from one server to a remote location. And while these are very resource intensive, it could very well happen that your host operating system might not leave enough free memory for the guest operating system of the virtual machine, which usually renders your VM not usable, or slows down your machine, your computer, your server so much that you would really not get much performance from the application running in the virtual machine. And then, of course, you have challenges of a 64-bit guest would not be able to run on a 32-bit host OS. And containers is the virtual appliances that we're talking about now. These are operating system level virtualization that allows multiple isolated user space instances called containers. They all share the kernel of the underlying host operating system. However, every container has its own OS, has its own minimum operating system to start with. Yes, with the containers, we do not install the full operating system. We just start with a image, a Docker image of a minimal operating system on which my software application can run. You can add, remove containers at any point in time. These are self-contained file systems, can be used from any Linux distribution like a CentOS or a Ubuntu or a Debian. And operating system level virtualization is far more lightweight than in hardware virtualization, which we were working with all these years. And these can be run on physical machines. These can be run on virtual machines. These can be run on virtual machines on the cloud as well. Docker is a containerization platform that lets you run, host, deploy, whatever terminology you want to use here, run containers. And containers provide us with a way to run software in isolation. So this is one of the challenges that I was talking on slide number 1. Anytime I would update one software or upgrade one software, something else would render not working, and I would have to either upgrade the other software also, or probably move it to a different server, a different machine that matched its software library binary operating system requirement. So what does a Docker container contain and provide? It is an operating system, a base operating system. It can be Linux, it can be Windows, and a bunch of software applications running on that. Now, these software applications are what you want to run in your container. If you were to deploy a software application in your production environment, the software application would have an operating system requirement. That software application would have some binaries, some libraries that need to be installed on that server along with that operating system. All of these I can include in my container. All of these I can add to my container, and that can become my container definition. That can become my Docker image, which is what is my container definition. Using that Docker image, I can run exact same container on any machine that I want, be it a developer's PC, be it a dev server or a test server, or even my production server. So our world, our life, software developers' life before Docker, before containerization looks something like this. We have our software code, we have specific configuration that needs to go with our software code. We use different tools like Jenkins or Vagrant and Chef to set up a server for us. It could be a dev server, test, or a production live server. And we take this code and the necessary configuration of this code, as well as the configuration of the machine on each of these machines every time our code moves from dev to test, test to UAT, UAT to prod. And a very common scenario, a very common situation here is a perfectly working code on a developer's PC would not work on a dev server, or something that is past testing on a development server would fail in UAT, or just before going live. And majority of times the reason for that is configuration of this code, or configuration of the underlying server. The configuration application is mostly done manually. Developers add softwares to their machines that they at times forget to mention in release notes, mention in configuration files, and that is what goes missing when that code is taken from one machine to another, and we find something that was working perfectly fine earlier has stopped working. Now, a software developer's life with Docker or with containerization would look something like this. You take your code, you take the necessary configuration, and you add that to a Docker image. You add the configuration of the machine, of the server, you add the configuration of this code into a Docker image. You use this image to deploy, to run a container on your development server, test server, and even release to production. Only thing you need on the underlying machine is an operating system and Docker. And it could be any operating system. I could be running a Windows application in my container on a Linux Ubuntu server and Docker installed on that. So we completely eliminate setting up our dev, our test, our production servers over and over again, most of the time repeating the same set of installations, the same set of configuration on each of these machines, deploying our code, testing our code, move everything to the next set of servers, deploy our code, test our code. Now I can bundle all of that in a container And I can take this container definition, I can take this Docker image, and using this Docker image, I can run the exact same container on a developer's PC as I can run in a production server. Docker works for pretty much all environments. You can install Docker in Linux, you can install Docker in OS 10, you can install Docker on Windows. This is a little bit about the architecture of Docker. So once I install Docker, I get a Docker host or a Docker daemon. It's a service. It runs as a service. And I also get a Docker client. I get a bunch of command lines that I can work with Docker. And from my command line, I issue commands. I send commands like Docker pull or a Docker build or a Docker run to my Docker daemon, to my Docker host. This Docker host is where the containers run, where my containers are deployed. Every container needs a Docker image to run. So when I give a command docker run, which is essentially a command to run a container, as we will see shortly, Docker would look for an image using which to run a container for which I give the docker run command. Now, there are a couple of different ways the Docker daemon would find this image. When I install Docker, I just install these two bits, the client and the host. Docker Registry is a repository for Docker images. Docker Hub is a public repository run by the company Docker. Anyone can use Docker Hub. It's a public repository. I think you can create one private repository in that. And if you want more than one private repository, you have to take some plans, purchase plans from Docker, or you can set up this registry on your network. You can set up a private Docker registry. Docker registry, like I said, is a repository for storing Docker images. When I issue a Docker run command to the Docker host, it would look for the image locally. If it finds the image locally, it'll take that image and run a container. If it doesn't find the image locally, by default, Docker would go to Docker Hub, the public registry. It'll look for that image on Docker Hub. If it finds that image there, it'll download that image locally and then run a container using that. Similarly, if I have a private registry, I do not want Docker to go to Docker Hub, I can specify that in my Docker run command. In that case, Docker would go to my private registry, download the image locally, and run a container using that image. Let's see a little bit of Docker in action and then come back and continue this. So this is my this is a Debian virtual machine I have running on Google Cloud. I already have Docker installed on that. I'm running a version 1.12.5 on this. And my command to look for images is Docker images. And I have a couple of images on my computer. I have a CentOS image. I have a JTrack image that I have created. Then I have a MySQL image that I downloaded from Docker Hub. Now, if I want a new image, Docker pull is the command I would specify to I would give to Docker daemon. So let's pull Docker pull. Let's pull Ubuntu. Why not? So this will pull the base Ubuntu image from Docker Hub. So it's pulling this image from Docker Hub. Let me also pull up Docker Hub in the meantime. We can take a look at Docker Hub together. So now if I check Docker images, yes, I have an Ubuntu image and its size is 83.49 megabytes. And this is how Docker Hub looks like. This is my account, but if you go to Explore, You can see all of these official images. So there's an image for Alpine, HTTPT, our dear Apache, Ubuntu. So this is the image I just pulled from Docker Hub when I gave the Docker pull command, and you can see there are images for a lot of different softwares, and these are all official images. There's an image for Ruby, OpenJDK, all of that. Yeah, so this is what my Docker Hub, this is what Docker Hub looks like. And like I was saying, I have an account on Docker Hub, and I have a bunch of images that I have created and published on Docker Hub. You could do the same. Anyone can use Docker Hub. So this is the image that we just pulled from Docker. This is an image of an operating system, Ubuntu. Just to look at the size of this operating system. 83.49 megabytes, and this is CentOS, the CentOS operating system, 199.7 megabyte. So this is where the first this is where the first catch of containers being lightweight starts from. The operating systems that we use, the operating system images that we use to run containers are very stripped down versions of operating systems. These are, the bare minimum, the basic of an operating system. This is the bare minimum CentOS files that are needed to run a CentOS machine. And if you ever wondered the size of operating systems that we've been installing all this time, which runs in a couple of gigabytes, if you ever wondered the software application that we write, that you write, I write, the software code that we write for our customers, do we really need the entire operating system to make that code run? Really not. We don't. However, this is how we have known operating systems to be distributed. This is the only way operating systems were distributed till now, except when we came to containers, when we came to operating system virtualization. Now we are looking at the smallest size of virtual machine, the smallest necessary size of virtual machine for me to run a container. Using that, of course, I can install whatever I want in that. I can install whatever libraries, packages I want to install in that. Let's quickly see if we can run a container using maybe a CentOS. So docker run is the command I would give to run a container. And so -it are the switches or options that I give to my docker run command that basically runs my container in an interactive mode, -i, and -t is for opening a pseudo terminal for me through which I can interact with my container. Let's give name to our container. I'm going to call it CentOS C1, and I want to use the image CentOS for running this container. And when my container is bash, when my container is run, I want Docker to open the Linux shell for me. Bin bash /bin/bash is the path to Linux shell. So docker run is the command that lets me run a container in an interactive mode with a pseudo terminal. And I want to name my container CentOS C1. I want to use the image CentOS, which I have here, you can see. And when my container is run, I want Docker to run the shell for me. So let's run this. Hello. I think I froze my screen. Hold on a second. Yes, I froze my screen. Not a problem. Just give me a minute. Let me open another one. Okay, are you back? Nope. All right. We'll send this guy away. We'll bring the other one. I really don't know. Okay, the other one is back up. So we'll close this guy. Yep, please leave. And this is the other one I have open. So Docker run -t name CentOS and bin bash. All right. So there you go. You can see my prompt has changed. I'm root inside my container. This is my container ID. So if I do a listing, I can do what's my present working directory, who am I? I logged in as root. I should have logged in as student, but that's all right, doesn't matter. And I can create a folder. I can create a file in that. I could do whatever I can do on a Linux CentOS machine inside my container. I can even do a yum install. Let's install which. I can even do a yum install inside my container. So from here onwards, it is a virtual appliance that has an operating system. I can create my own folders. I can create my own files. I can install softwares in that. Okay, wait. And now, if I list, this is the container I was just running. So this is the container ID. This is the image. This is the command I gave it. It was exited 4 seconds ago, and CentOS C1 is the name I gave to my container. Right. So in this case, we used a container image that we pulled from Docker Hub. We took a CentOS image from Docker Hub and we ran a container on top of that. Let's quickly see if we can create our own image. And all right. Yeah. So I have a Docker file that I can use to create my own custom image. Dockerfile is an automated way, way of creating my own custom images, my own Docker images. So the little exercise we did just now, we just took an image, a pre-created image from Docker Hub, and we ran a container. So that's all good, wonderful. I mean, I'm writing my own software application. How do I make use of Docker? For me, that is not enough. I should be able to run my own software application in a container. And for that, I need to create my own Docker image. And you can create your Docker image manually in an interactive mode. The way I just did, I did a yum install inside a container, or I can automate my image creation. And in order to automate my image creation, we write a Docker file. We create a Docker file in which, essentially, if you see, these are just steps that I want to follow to create my container. So I want to create my container from Alpine. Alpine is a Linux distribution. From Alpine base image, I want to add OpenSSH to that. So APK is the installer package for Alpine, like Yum is an installer package for CentOS. So I want to do an APK add OpenSSH. Then I want to add a user. All of this I'm adding to my container. I'm not adding to my computer. All of this is my image definition. All of these steps are going to be part of my image definition. I'm adding a user, I'm changing the password of that user, I'm adding authorized keys, which are my set of my public keys to my container. I will use my private key to make a connection to this container. Like today, I make a connection to a remote machine. So I've added my public key into authorized keys, which I'm adding to my container. I'm making the user student as the owner of home student folder. I'm changing some folder permissions. I'm exposing a port on my machine where my container will be running, and I'm basically running the SSHD service inside my container. Now I can use this and build a Docker image, build my own Docker image, and Docker has a command for that, Docker build. I can tag my image and I can call my image, let's call this SSH Alpine. And I want Docker to look for the Docker file in this folder where I'm running this. So this will take about 10-20 seconds to finish. Yes, disabled. Hang on a second. Wait a second. Something is not right. I'm just opening a new terminal because I should not be getting that error. IPv4 error. Okay, we have a new one. All right, I don't know. I think I should not have deleted that. I should not have closed that terminal. That's all right. I have another Docker file that we can take a look at. And thankfully, I have an image for this. So hopefully this one should not have an IPv4 problem. So this is another Docker file I have for creating an image for a software called JTrack. This one I'm creating from CentOS. I'm installing wget in that. I'm installing zip in that. I'm basically downloading Java, the JDK, from Oracle's website. So I'm downloading the JDK RPM. I'm running the RPM command for that. I'm setting my Java home. I'm then downloading JTrack. JTrack is actually an application for it's an open source Java project you can use for tracking your issues, defects. You can even use it for tracking tasks of your project. So I just decided to add this in a container. And I'm installing unzip. I'm unzipping. So this JTrack installer is a zip actually. If I go back. JTrack here. So there you go. So that's the reason I'm installing unzip. I'm unzipping that. I'm moving basically the start batch file to start shell. I'm deleting the RPM and zip. I'm changing my working directory to JTrack, and I'm running the start SSH, sorry, start SH, the shell. And if I run a docker build -t JTrack, it'll give me an image. Luckily, I have that image. So this is the image it will create for me. So this is the JTrack image for the Docker file that we just saw, that we just went through. This was the Docker image for that. Now I can use my image and run a container. I can use my image to run a container, and I would use the Docker run command for that. And to run this container, I'm going to run it in a daemon mode. I'm going to have it keep running. So I'm going to call my container JTrack. I'm going to make it available on port 8080, and port 80 is where my container is available. Port 8080 of my host is where I'm going to make the application JTrack available for external users, and I'm going to use the image JTrack to do that. Is already in use by container. Docker PS, do I have JTrack running? Yes, I have JTrack running. So let me do this. Let me stop JTrack. It's a container, so we're going to stop the container and we're going to run it again. All right. Docker RM. We're going to run a new container with the same name, so that's the reason. Okay, Docker PS. And there you go. So this is the JTrack container we just started. It's been up since 3 seconds. It's using the image JTrack, and it is available on port 8080 of my virtual machine. So let me find out port 8080 of my virtual machine. So my VM is on this IP, 8080 and JTrack. Yep, it is running. I'm going to try it one more time. Otherwise, I'm going to probably, yeah, we'll do one thing. We will stop my VM and start it again. In the meantime, let's take a look at, yeah, this is the hands-on we were taking a look at. Similarly, um, I can even run my Docker registry, my own Docker registry, private registry, in a Docker container that I can use to store my images, to keep my images, the images that I create. And Docker Hub is not the only public registry. Google has a Docker registry. Amazon EC2 has a Docker registry. Key is another public registry that you can pay for different plans. And you will run your own private registry, for storing your images, for pulling images from your uh, from your projects to a private registry. And of course, this way you can be sure that you have the necessary security. It's your Docker images are not on a public repository where, which is something that our customers many times are not very okay with. So private registry could be one thing that you could go for. Docker also lets you create or use Docker data volumes to store any data created within your containers to a storage location outside your containers. And a data volume is essentially a directory structure that is mounted into a Docker container. Of course, this doesn't become part of your Docker container. It's an external folder, external file system that is mapped to a folder inside your container. And all the data your application is generating, all the data, all the files your software application is generating gets written to this data volume, which can be accessed, which can be made available to other applications, to other users. Docker also enables networking. Docker also lets you network different containers in the kind of architectures that software architecture that we use is end-tiered, where you have an application server, you have a web server, we have a database server, and you typically set up networking amongst these servers. Now, if I were to use Docker containers to do the same thing, then my web components would be running in a container, my server components would be running in another container, and my database could be running in a third container. Now, I would want to network these containers also for my software application to be complete, for my software application to be working. And that is where you can network Docker containers. So Docker provides us with certain default networking, a bridge network, a host network, and I can create my own user-defined networks also in Docker. If I quickly go back to my terminal, no, we'll open a new one because I restarted my virtual machine. So I'll show you that when my terminal shows up, that these are the three network types that Docker provides me, and I can create my own user-defined network, which will be of type bridge. This basically allows me to network my containers, share IP addresses amongst my containers. Yes, every container has an IP address. And for clustering containers in production servers, for creating many different containers or many containers of one application, for scaling up purposes, for load balancing purposes. Docker provides us with tools like Swarm, Compose, that allow us to create clusters of containers, and you can manage, maintain all these containers from a single cluster machine, from a single swarm manager, instead of like today, we would not log into each and every server in production to issue a set of commands on that server. We usually have a commanding terminal or a machine that gives us an overview of our entire infrastructure, all the servers, all the applications running in the servers. Likewise, in the world of Docker, we have applications like Swarm, Compose, Kubernetes that let us do the same, that let us spin new containers, that let us start, stop containers, that let us view what is running inside a container. Um, that lets me install software in a container from a single console, not having to go to each and every machine and then do a Docker run. Instead, I can cluster my containers. And Swarm uses a Swarm uses a Swarm manager. Swarm manager is the machine from where you can manage your entire container cluster. A similar tool is Compose, which is again used for running multi-container applications. A single machine can run multiple containers on different hosts. A single Compose can manage multiple containers running on different host machines. It can start, stop containers. It can rebuild services inside containers. Lets you view status of running applications, running services inside the container, and even view the logs of any running services. Container as a service is also a cloud offering that is, now provided by many cloud providers. So container as a service is a form of container-based virtualization in which your container engine, orchestration, and the underlying compute resources are delivered to users as a service from your cloud providers. In some cases, container as a service is also used to describe a cloud provider's container support services. So with this, you can upload, you can organize, run, scale, manage, stop containers using a provider's API calls or a web portal's interface. So as is the case with most cloud services, users pay only for the container as a service resources like your compute instances, your load balancing, your scheduling capabilities that they are using. And within the spectrum of cloud computing services, container as a service falls somewhere between infrastructure as service and platform as service. However, container as service is most commonly positioned as a subset of IaaS, infrastructure as service. And your public cloud providers, including Google, AWS, Amazon Rackspace, Joint, all have some type of container as a service offering. For example, AWS has its Amazon EC2 container service, which is a very high performance container management service for Docker containers. And Amazon ECS eliminates the need for users to have any in-house container or cluster management resources. And yeah, Docker has a universal control plane. Core OS Tectonics also has container as service available. Google Cloud Engine we just talked about. There's a project Magnum. It's an OpenStack API service that also enables container orchestration for Docker, even for Kubernetes. Kubernetes is, again, one of the tools used in production setup for container orchestration. Container orchestration is essentially starting new containers, stopping containers, restarting containers, creating new images of containers, and all of that good stuff. So it's also called Kate. It's an open source tool used for automating your container deployment, container management, scaling. It was designed by Google. It automates your deployment. It automates your container scaling, even operations of applications running inside containers. And this is something as old as just 3 years old. And Kubernetes is a very, very popular tool platform used in the container space. So that's all I think I wanted to talk about for containers today. And if you guys have any questions, you can post them in the chat window. Sorry about the technical goof up that my virtual machine is having, and I have no idea why. And trust me, I tested this before getting into this session, but yeah, I would do is when I share the handout with you, I'll probably share the setup instructions for that if any one of you is interested in doing that. Or I'll probably do is I'll take some screenshots of the working JTrack and stick it in a Word document and send it to you. But yeah, that was unfortunate and really sorry about that. Do we have any questions? If you guys have any questions, please feel free to post them. And thanks everyone for joining. I hope this was helpful. It got you some idea of what containers are, how you can use them, and all of that. Yeah, you can write to training at DevLabsAlliance.com if you guys have any questions or if you want to reach out in future. And I will have the handouts sent across to you guys shortly. All right, thank you very much. Thanks everyone for joining. I think we can close for the day. Sorry for going over a couple of minutes, our session time, but great. Thanks a lot. Thank you very much.